Hello. In the previous episode, I introduced density functional theory, and if you haven't watched that episode, you should go back and watch that before you watch this one. So we introduced density functional theory, specifically the Hohenberg-Kohn theorems. Now, the first Hohenberg-Kohn theorem is merely an existence proof for the energy functional. It tells us that an energy functional exists, but it doesn't tell us what it is or how to go about finding it. The second Hohenberg-Kohn theorem is merely a variational principle for the energy. Now, if Walter Kohn had been a pure mathematician, he might have been satisfied with this and stopped and gone on to other things. But of course, he was a physicist and an applied mathematician. So his interest was in finding a practical way to calculate the energies of electronic systems. So let's talk a little bit about Walter Kohn. Walter Kohn was born in Vienna in 1923 to Solomon and Gittel Kohn. Gittel's parents were Orthodox Jews. Solomon ran a business producing and selling art postcards. Gittel was highly educated with a flair for languages. At the Akademie Gymnasium, Walter's favorite subject was Latin. Mathematics earned him his only C. Following the union or Anschluss of Austria with the German Third Reich in 1938, the Kohn family business was confiscated and Walter was expelled from school. His sister Minna managed to emigrate to England, and Walter too managed to emigrate in August 1939, but Solomon and Gittel were unable to leave Austria and were murdered during the Holocaust. In May 1940, Churchill ordered male enemy aliens to be interned, and thus Walter found himself at the age of 17 interned in various camps before being shipped off to Canada. Walter studied physics, chemistry, and mathematics at camps in Quebec and in New Brunswick with the help of camp educational programs taught by other internees. Saving money working as a lumberjack, he was able to buy textbooks in mathematics and chemical physics and passed McGill University's junior matriculation exam. Upon his release from internment in January 1942, Walter began attending the University of Toronto, but was not allowed to enroll in chemistry courses on account of his German nationality. After 2.5 years in the undergraduate program, while also serving at the same time in the Canadian Army, Walter received a bachelor's degree in applied mathematics and then a master's. He then joined Harvard with a Lehman Fellowship for a PhD under Julian Schwinger. Here, Kohn developed a variational principle for three-body scattering and receiving his PhD in 1948. Kohn taught solid-state physics first at Harvard, then at the Carnegie Institute of Technology, now known as Carnegie Mellon University, and moved to the University of California at San Diego in 1960. He spent a sabbatical semester, the fall of 1963, at the École Normale Supérieure in Paris, where he became interested in the concept of the effective charge of an atom in an alloy. Wondering whether an alloy is characterized completely or only partially by its electronic density distribution, Kohn proved that the external potential V of R is determined within a trivial additive constant by the distribution of electron density rho of R, thus establishing an existence theorem for the unique energy functional E of rho of R for a non-degenerate ground state by reductio ad absurdum. Kohn then set his new American student in Paris, Pierre Hohenberg, to prove a variational principle for the energy functional E of rho of R. So thus far we have covered in the previous episode. Now, upon his return to San Diego in 1965, Kohn and his postdoctoral student Lou Sham derived a set of one-electron equations for the density. We shall pick up the story here, but before we talk about the Kohn-Sham equations, it is first necessary to discuss the exchange correlation hole. Let's first talk about the kinetic energy. Why can't the kinetic energy functional be simply written in terms of the del squared rho? Well, the kinetic energy operator is T equal to minus half sigma I del I squared. For a one electron function, rho is equal to psi star psi, and therefore del squared rho can be obtained by differentiation to give us this formula. And if psi is real, that just reduces to 2 psi del squared psi plus 2 del psi dot del psi. If we put that in the expression for the kinetic energy, minus half psi star del squared psi, we obtain minus a quarter del squared rho plus half del psi dot del psi. This is known as the Weizsäcker kinetic energy formula. So we see that the kinetic energy is not just minus a quarter del squared rho, but also has this plus half del psi dot del psi term. For many electron wave functions, it is more complicated, since rho is not just psi star psi, but is psi star psi integrated over n minus 1 electrons. Now, why can't the interelectronic repulsion be written simply as half integral d tau dash rho of r times rho of r dash by modulus of r minus r dash? Well, the actual interelectronic repulsion is half integral d tau dash gamma of r and r dash by modulus of r minus r dash, where gamma is the pair density, which is obtained by integrating psi star psi over n minus 2 electrons, and it gives the probability of simultaneously finding an electron at the point r within volume element d tau and another electron at the point r dash within volume element d tau dash. Thus, the Hartree part of the interelectronic repulsion is half integral d tau dash rho of r times rho of r dash by modulus of r minus r dash, which is different from the actual interelectronic repulsion. If the motions of the electrons were not correlated, the classical simultaneous probability of finding an electron at r and another at r dash is simply the product of the individual probabilities, that is rho of r times rho of r dash. So the Hartree interelectronic repulsion is just given by the integral of that divided by the interelectronic distance, that is half integral d tau dash rho of r times rho of r dash by modulus of r minus r dash. But electrons obey Fermi-Dirac statistics. Electrons with the same spin are kept apart by the Pauli exclusion principle. Furthermore, due to Coulomb repulsion, even electrons of opposite spin avoid each other better than in the average Hartree description. Thus, each electron reduces the probability of finding another electron around it, creating a depletion or hole in the electron density around itself. This is the exchange correlation hole with a density rho exchange correlation of r and r dash. And since it is a hole, that is, it's a depletion in the electron density, it has a negative density. The quantum mechanical pair density can be written in terms of the exchange correlation hole as gamma of r and r dash is equal to rho of r times rho of r dash plus rho of r times rho exchange correlation of r and r dash. Since the exchange correlation hole excludes electron density from the space around it, it is, as we have seen, a negative quantity. Due to normalization, every electron is surrounded by a hole in the electron density of equal and opposite charge, that is integral d tau dash rho exchange correlation of r and r dash is equal to minus 1. This normalization condition is known as the sum rule. The exchange part of the hole, that is known as the Fermi hole, has a charge of minus 1. That is, due to the Pauli principle, every electron excludes one electron of the same spin from the space around it. while the correlation part of the exchange correlation hole, known as the Coulomb hole, has a net charge of 0. That is, due to Coulomb repulsion, any electron density that is repelled from the space immediately around an electron has to go somewhere. It's like digging a hole in the ground. Whatever mud you take out of the hole, you have to pile it up somewhere away from the hole. So the Fermi hole is nothing but the physical manifestation of the Pauli exclusion principle. It describes how the density of a reference electron at any point in space spreads out into the space of another electron of the same spin, thereby excluding an identical amount of same spin density. The Fermi hole is the electron's doppelganger, that is, it shadows the electron's motion and goes wherever the electron goes. If the electron is localized, so is its Fermi hole, and when the electron is delocalized, so is its Fermi hole. The Fermi hole integrated over all space corresponds to removal of one electronic charge of the same spin. That is, the integral of the Fermi hole density over all space equals -1, as we have seen. The density of the Fermi hole at the position of the reference electron is the negative of the total density of same spin electrons. That is, the rho exchange alpha of R and R is minus rho alpha of R, ensuring that there is zero probability of finding another electron of same spin at the position of the reference electron. Now consider a fictitious system of n non-interacting electrons that is designed to have the same density as the real interacting system. So the Hamiltonian of this fictitious non-interacting system is just H0 equals T0 plus V. There is no U term since the electrons are non-interacting. The kinetic energy of this fictitious non-interacting system T0 is given by the sum over the occupied orbitals of -12 bra phi k del squared phi k ket. Since the kinetic energy is a sum of one electron operators, as is the electron nuclear attraction V, the many electron wave function can be constructed as a normalized Slater determinant of eigenfunctions phi k with the n/2 lowest eigenvalues. The eigenvalue equation is then -12 del squared plus V of R operating on phi k gives epsilon k times phi k. The densities of the occupied orbitals phi k sum up to give the true electron density of the real interacting system, since our fictitious system has been designed to have the same density as the real interacting system, and the density rho of R is then sum over the occupied orbitals of phi k of R modulus square. Then the universal functional f of rho is then given by T0, the non-interacting kinetic energy, plus the classical interelectronic Coulomb repulsion energy, or the Hartree term, plus E exchange correlation of rho of R, which contains the difference between T minus T0 and also the non-classical part of the interelectronic repulsion U. If we substitute this in the last term here, we see that T0 cancels out and the Hartree term also cancels out. So we just are left with F equals T plus U. Now let us turn to the real interacting system. The energy functional for the real interacting system is E of rho equals T of rho plus integral V of R rho of R d tau plus half integral d tau dash gamma of R minus R and R dash divided by modulus of R minus R dash. But we have seen that gamma of R and R dash is equal to rho of R times rho of R dash plus rho of R times rho exchange correlation of R and R dash. So E of rho is equal to T of rho plus integral V of R rho of R d tau plus the Hartree term plus the exchange correlation energy. This part of the equation, that is excluding the exchange correlation term, this part of the equation is a set of equations for independent particles and is therefore easily soluble. This term is the unknown exchange correlation functional. It is defined in terms of the exchange correlation whole, rho exchange correlation of r and r dash. Thus, E exchange correlation of rho of r is equal to a half integral d tau dash rho of r times rho exchange correlation of r and r dash divided by modulus of r minus r dash. We can then write the Kohn-Sham equations in terms of a Kohn-Sham effective potential Vks of r. So thus minus half del square plus Vks operating on phi k of r equals epsilon k times phi k of r, where the Kohn-Sham effective potential Vks of r is equal to Ve of r, the electrostatic potential, plus V exchange correlation of r, where the electrostatic potential is given by the external potential V of r plus the electrostatic potential due to the electrons, integral d tau dash rho of r by modulus of r minus r dash. The exchange correlation potential V exchange correlation of r is the functional derivative of the exchange correlation energy with respect to the electron density. So what has been achieved? The solution to the interacting many electron problem has thus been reduced to finding a good approximation to the unknown exchange correlation term. It is either the exchange correlation energy or the exchange correlation potential, followed by solving a set of one electron equations, the Kohn-Sham equations, minus half del square plus Vks operating on phi k equals epsilon k times phi k. Kohn and Sham thus obtained a practical recipe for obtaining the electron density and the total electronic energy, formulating a theory going beyond the Hartree-Fock treatment by including electron correlation, but at the cost of solving a set of one electron Kohn-Sham equations. Okay, thus the computational cost is more or less the same as Hartree-Fock, but since the effective potential includes the exchange correlation term, they have gone beyond the Hartree-Fock treatment and included electron correlation, thus obtaining a more accurate treatment for interacting many electron systems. So to summarize the Kohn-Sham procedure, we start by choosing an exchange correlation energy functional, specifying the geometry, charge and multiplicity, selecting a basis set phi for expansion of the orbitals, psi k equals sigma j psi ckj phi j. We guess an initial density, use that density to calculate the exchange correlation potential by taking the functional derivative of the exchange correlation energy with respect to the density. Use rho and Vxc to calculate the Kohn-Sham operator minus half del squared plus Vks of r, where the Kohn-Sham effective potential Vks is V of r plus integral d tau dash rho of r by modulus of r minus r dash plus V exchange correlation of r. Calculate the Kohn-Sham matrix elements, that is the matrix elements of HKS between the Kohn-Sham orbitals. Diagonalize the Kohn-Sham matrix to get the coefficient Ckj and that we used in the to expand the orbitals, and thus to obtain the Kohn-Sham orbitals psi k. The eigenvalues are then the Kohn-Sham orbital energies. Use these orbitals to construct an improved density rho of r equals sum over the occupied orbitals psi k of r modulus squared. Return to step 5 and continue until self-consistency, that is, use this density to calculate a new exchange correlation potential, a new Kohn-Sham operator, a new effective Kohn-Sham effective potential, and calculate the matrix elements of the new Kohn-Sham operator, diagonalize that Kohn-Sham matrix to get the coefficients and the new orbitals, and use those new orbitals to get a new density, and so forth. Continue the procedure until self-consistency. Then finally compute the total electronic energy through this expression. So, how good is all this? How much better than Hartree-Fock? To quote from a 1992 paper by Popel and co-workers, in summary, these initial results indicate that density functional theory is a promising means of obtaining quantum mechanical atomization energies. Here, the DFT methods BVWN and BLIP outperformed correlated ab initio methods, which are computationally more expensive. Good agreement with experiment was obtained with a small basis set. And in the following year, they reported the density functional vibrational frequencies compare favorably with ab initio results, while for atomization energies, two of the density functional methods gave excellent agreement with experiment and are clearly superior to all other methods considered. This led to award of the 1998 Nobel Prize for Chemistry to Walter Kohn for his development of the density functional theory, and to John Popel for his development of computational methods in quantum chemistry. Density functional theory became popular among chemists after John Popel incorporated the DFT codes into his Gaussian suite of programs in the early 1990s. As you can see, starting in the early 1990s, there was a sharp jump in the number of papers employing density functional theory, and since then the number of papers using DFT has been exponentially rising. As Kieran Burke remarked in 2012, it is clearly the best of times and the worst of times for DFT. More calculations, both good and bad, are being performed than ever. As Mike Frisch, the CEO of Gaussian, points out, regardless of what functional you use and what property you want to calculate, density functional results are always better than Hartree-Fock. We will stop here today, and next time we will talk about Jacob's ladder of density functionals, which is a systematic way to improve the quality of density functionals for more accurate results. See you next time.